The digital transformation of power systems brings both unprecedented opportunities and serious vulnerabilities. As transmission and distribution networks integrate advanced communication systems, intelligent electronic devices (IEDs), and decentralized energy resources, the risk of cyber intrusion grows exponentially. In this video we explores the technical underpinnings of cybersecurity in power grids, examines emerging threats and vulnerabilities, evaluates innovations in cybersecurity for grid modernization, and proposes a strategic framework for safeguarding the grid. The electric grid's digital transformation has unlocked greater efficiency, visibility, and renewable integration but also broadened the cyber attack surface. Below is a deep dive into the technical foundations of power system cybersecurity, the evolving threat landscape with real-world examples, and a multi-layered defense framework to safeguard critical infrastructure. Cybersecurity is the science and practice of defending digital systems, data, and infrastructure from unauthorized access, attack, or damage. In the context of power systems, it encompasses securing operational technology (OT), such as substations, SCADA, and protection relays, as well as information technology IT systems like databases, control center networks, and cloud platforms. Cybersecurity is the discipline of protecting digital systems, networks, and data from unauthorized access, misuse, or damage. It involves both preventive and responsive strategies to ensure that sensitive information and essential infrastructure remain secure and functional. Key objectives: confidentiality, prevent unauthorized access to operational data. Integrity, ensure data and system commands are not tampered with. Availability, ensure continuous, reliable access to systems. Cybersecurity ensures secure delivery of electricity, protects public safety, and maintains national security. In the power sector, cybersecurity plays a vital role in protecting both operational technology. This includes systems directly involved in power generation, transmission, and distribution, such as SCADA supervisory control and data acquisition systems, substation automation systems, protection relays and remote terminal units, intelligent electronic devices, information technology. These systems manage data and communications, including control center servers and databases, utility, enterprise networks, cloud-based platforms, and remote access systems. Cybersecurity is built upon three fundamental pillars, often called the CIA triad: confidentiality, preventing unauthorized users from accessing sensitive operational or customer data; integrity, ensuring that data e.g., measurements, commands, and logs remains accurate and unaltered by malicious or accidental actions; availability, guaranteeing that critical systems like SCADA and control centers are continuously accessible to authorized operators, even during cyber incidents. Effective cybersecurity in power systems is essential because it protects public safety. A cyber attack on a grid could lead to blackouts, equipment damage, or even hazards to human life. Ensures reliable power delivery. Maintaining uninterrupted electricity service depends on secure and stable digital infrastructure. Safeguards national security. Power grids are part of a nation's critical infrastructure, making them targets for cyber warfare or terrorism. Cybersecurity refers to the protection of digital assets such as hardware, software, and data from unauthorized access, alteration, or disruption. In modern power systems, which increasingly rely on digital technologies, cybersecurity is essential to maintaining safe and reliable operation. Cybersecurity protects digital assets, hardware, software, and data from unauthorized access, alteration, or disruption. In power systems, it spans two domains: information technology, data centers, and enterprise networks, cloud platforms, and analytics services. Operational technology, SCADA, energy management systems, intelligent electronic devices, RTUs, and substation automation. Core objectives: confidentiality, prevent unauthorized reading of system configurations or grid data. Integrity, guard against undetected modification of measurements or control commands. Availability, ensure continuous monitoring and real-time control access. Power system cybersecurity underpins not only data protection but also grid reliability, public safety, and national resilience. Two main domains of power system cybersecurity. Cybersecurity in the power sector applies to both information technology and operational technology. Information technology: this domain handles the data processing and communication infrastructure of the utility, including Data centers and enterprise IT networks, cloud computing platforms and analytics services used for data storage, billing, customer management, and decision support. While operational technology, this domain includes the real-time control and automation systems used to operate the electrical grid, such as supervisory control and data acquisition and energy management systems, intelligent electronic devices, remote terminal units, and substation automation systems. OT systems interact directly with grid equipment and are often time-sensitive and safety-critical. Cybersecurity in power systems is not just about protecting data, it directly affects grid reliability, ensuring that the power supply remains stable and uninterrupted, public safety, preventing scenarios where cyber attacks could cause blackouts or equipment failures with hazardous consequences, national resilience, securing critical infrastructure against state-sponsored attacks, terrorism, or sabotage. As grids digitize, cyber threats join traditional contingency storms, equipment faults as primary risks to protection schemes. Key threat vectors, malware and ransomware, targets control servers to lock operators out or extort payment. Phishing and insider threats, harvest credentials or trick staff into installing backdoors. Remote access exploits, leverage unsecured VPNs or vendor portals for initial entry. Command injection and data spoofing, manipulate breaker commands or falsify sensor readings. Grid protection is no longer limited to physical devices like relays and breakers. It now includes cyber protective measures that secure the digital control layer of the power grid. As modern grids become increasingly digitized and interconnected, they are also more exposed to cyber threats that can disrupt operations, damage equipment, or even compromise national security. Grid protection includes cyber protective measures that guard the digital control layer of the grid. Modern threats range from malware to advanced persistent threats. Cyber threats, malware, ransomware, phishing, insider threats, remote access exploits, command spoofing and injection. Real incidents like the Ukraine grid attack show the potential impact. Protection involves hardened OT systems, encrypted protocols, and continuous monitoring. Cyber threats targeting power systems can take many forms, including malware and ransomware. Malicious software that can disable systems, encrypt files, or allow remote control by attackers. Phishing and insider threats, deceptive emails or actions by employees, intentional or accidental, that give attackers access to internal systems. Remote access exploits, vulnerabilities in remote access tools, VPNs, remote desktops used by vendors or engineers that attackers can hijack. Command spoofing and injection attacks, fake or altered control commands injected into the network, potentially causing unsafe switching or equipment tripping. In 2015, Ukraine experienced a major cyber attack on its power grid. Hackers gained remote access to control systems, opened circuit breakers at substations, and caused large-scale blackouts. This real-world incident showed that cyber attacks can cause physical outages, operational technology systems are vulnerable, while coordinated attacks can bypass traditional defenses. To defend against such threats, utilities implement layered protection strategies, hardened OT systems, secure configuration of SCADA, EMS, and substation devices, e.g., disabling unused ports and services, encrypted protocols, use of secure communication channels, e.g., TLS, VPNs to protect data in transit from interception or manipulation. Continuous monitoring, real-time detection of anomalies using intrusion detection systems, security information and event management, and logging of suspicious activity. Why it matters: cybersecurity and grid protection is essential to maintain safe and stable grid operations, prevent blackouts, equipment failures, or public safety incidents, protect critical national infrastructure from increasingly sophisticated cyber adversaries. In December 2015 and again in 2016, coordinated intrusions into Ukraine's grid SCADA enabled attackers to open circuit breakers at multiple substations, plunging hundreds of thousands into darkness. Sophisticated reconnaissance, spear phishing, and custom malware, e.g., black energy, were all employed to bypass protections and manipulate relay operations. Protective measures: hardened OT networks with strict access controls and signed firmware, encrypted SCADA protocols, e.g., IEC 62351, TLS, industrial-grade IPS tuned for protocol anomalies and command misuse, continuous monitoring of user behavior and endpoint integrity. One of the most significant cyber attacks on a power grid occurred in Ukraine in 2015, followed by a similar attack in 2016. These incidents serve as clear warnings of how vulnerable power infrastructure can be to cyber threats when digital systems are compromised. What happened? In December 2015, attackers remotely accessed SCADA systems used by Ukrainian utilities. They opened circuit breakers at multiple substations, cutting power to over 230,000 people for several hours. In 2016, a more advanced cyber attack caused an automatic blackout in part of Kiev using in-destroyer crash override malware, capable of speaking industrial protocols directly. The attackers used a coordinated and multi-layered strategy, including spear phishing, targeted emails sent to employees with malicious attachments, tricking them into opening the door for malware. Black Energy Malware, a custom-built malware tool used for espionage and remote access to control systems. Reconnaissance, attackers spent weeks or months studying network layouts, user behaviors, and system operations before executing the final action. Relay manipulation, the attackers sent malicious commands to protection relays, manually opening breakers and corrupting firmware in some cases. To prevent such sophisticated attacks, power system operators can implement the following cybersecurity defenses: hardened OT networks, enforce strict access controls, only authorized personnel should be able to access critical systems. Use signed firmware, ensures that only verified, untampered firmware can be installed on devices. Encrypted SCADA protocols, implement security standards like IEC 62351, adds authentication and encryption to IEC protocols. Transport layer security, secures communication between SCADA components and control centers. Industrial-grade IPS, deploy intrusion detection and prevention systems customized for industrial environments. These tools monitor for protocol anomalies, suspicious command sequences, and unusual behavior in OT systems. Continuous monitoring and endpoint security, monitor user behavior e.g., login patterns, access times for signs of compromise. Regularly verify the integrity of endpoints, such as control room PCs, engineering workstations, and field devices. The Ukraine grid attacks exposed how unsecured digital systems in critical infrastructure can be weaponized. They highlighted the need for defense in-depth strategies, cross-discipline collaboration between IT and OT teams, proactive monitoring and response capabilities. Investing in robust cybersecurity is no longer optional. It is essential to maintain the reliability and safety of modern power systems. Modernization deploys devices that enhance situational awareness and flexibility but create new vulnerabilities. Technologies involved: phaser measurement units for wide area synchrophosor data, smart meters and advanced metering infrastructure. Distributed energy resources like rooftop solar and battery storage, IoT sensors for substation environmental and asset health monitoring. Grid modernization and its cybersecurity implications. As power systems evolve to become smarter, more efficient, and responsive, utilities are deploying a wide range of digital and intelligent technologies under the umbrella of grid modernization. These advancements bring major operational benefits, but they also introduce new cybersecurity risks that must be addressed. Modern grid infrastructure integrates advanced tools and systems to improve visibility, flexibility, and reliability. Key technologies include phaser measurement units, provide real-time synchrophosor data across wide areas, enhance situational awareness, event detection, and stability analysis, require high-speed, secure communication networks due to their sensitivity and real-time nature. Smart meters and advanced metering infrastructure enable two-way communication between utilities and consumers, support time-of-use pricing, remote disconnection, and outage detection. However, millions of connected devices increase the cyber attack surface, especially if not securely configured. Distributed energy resources include rooftop solar panels, wind turbines, battery storage, and EV chargers, often connected via third-party networks or internet-facing protocols, can be exploited to destabilize grid operations if improperly secured or coordinated. IoT sensors in substations, used for monitoring equipment health, temperature, humidity, and other environmental conditions, help in predictive maintenance and improving asset management. However, many low-cost IoT devices lack robust security features and can be entry points for attackers. While these technologies enhance operational capabilities, they also create new cybersecurity challenges. Expanded attack surface, more devices and endpoints mean more potential vulnerabilities. Interconnected systems, a compromise in one device e.g., smart meter or IoT sensor can provide a pathway to higher-level control systems. Data authenticity risks. If PMU or AMI data is tampered with, it can mislead operators and cause incorrect decisions. Need for real-time security. Many modern devices operate in time-sensitive environments where delays or false signals can have serious consequences. Every new digital device or connection point must be viewed not only as an operational asset but also as a potential cyber vulnerability. Securing this modern grid requires end-to-end encryption, device authentication, network segmentation, continuous monitoring, vendor and supply chain risk management. Grid modernization integrates advanced digital technologies for enhanced control and resilience. Components include smart meters, PMUs, DERs, and IoT sensors. Challenges: legacy equipment with weak security, more devices equal to more vulnerabilities. Cloud SCADA and remote firmware updates pose risks. Cybersecurity must be embedded at every level, using zero-trust principles and secure architectures. Grid modernization is the transformation of the traditional power grid into a more intelligent, flexible, and resilient system by integrating advanced digital technologies. These technologies enhance real-time control, situational awareness, energy efficiency, and response to dynamic grid conditions. Modernized grids incorporate the following key technologies. Smart meters enable two-way communication between utilities and consumers for better demand response, billing, and outage detection. Phasor measurement units provide synchronized, high-speed voltage and current data to improve grid visibility and stability. Distributed energy resources include rooftop solar, battery storage, electric vehicles, and small wind systems that feed power back into the grid. IoT sensors monitor environmental conditions and asset health, e.g., transformer temperature, humidity, oil level in real time for predictive maintenance. While grid modernization improves operational performance, it introduces new cybersecurity challenges, including legacy equipment with weak security. Older systems were not designed for internet connectivity or cyber resilience. These legacy devices may lack encryption, authentication, or even basic access control. Increased number of devices equal to larger attack surface. More connected devices, meters, sensors, DER inverters mean more potential entry points for cyber attacks. A compromised device could serve as a pivot point to reach critical control systems. Cloud-based SCADA and remote firmware updates. Moving control systems and data storage to the cloud increases efficiency but introduces new risks, such as unauthorized access, firmware tampering, cloud misconfigurations. To counter these risks, cybersecurity must be embedded at every level of the modern grid, not added as an afterthought. Key security approaches: zero trust architecture, never trust, always verify. Every user, device, and application must prove identity and authorization before gaining access, regardless of location. Secure by design. Systems, devices, and networks should be designed from the outset with built-in encryption, authentication, and access control. Defense in depth. Use multiple layers of protection, e.g., firewalls, IDS, endpoint monitoring, so that if one layer fails, others still protect the system. Grid modernization is essential for meeting future energy demands and enabling clean energy integration, but it must be matched with strong cybersecurity. Without it, the same technologies that make the grid smarter could also make it more vulnerable. Digitalization has transformed power systems into complex cyber-physical networks, and with that comes an expanded threat horizon. Embedding cybersecurity as a foundational element of grid design and operations, bolstered by advanced analytics, secure architectures, and institutional preparedness, is non-negotiable. Only through continuous assessment, layered defenses, and proactive innovation can utilities ensure reliable, safe, and secure electricity delivery in the digital age. Digitalization has turned power systems into intricate cyber-physical networks, significantly expanding their exposure to cyber threats. To protect these critical infrastructures, cybersecurity must be deeply integrated into every aspect of grid design and operations. This integration should be supported by advanced analytics, robust secure architectures, and strong institutional readiness. Utilities can only guarantee reliable, safe, and secure electricity delivery by continuously assessing risks, implementing multiple layers of defense, and embracing proactive innovation to stay ahead of evolving cyber challenges in today's digital landscape.